Two cells of EMF 2 volt and 1 volt, internal resistance 1 ohm and 2 ohm have their positive terminals joined by a wire of 10 ohm and their negative terminals by a wire of resistance 4 ohm. A resistance of 10 ohm joins the midpoint of these two wires. Calculate the PD between the ends of the wire. So let us draw the circuit, okay, of this problem, okay. So we have two cells. So I'm drawing cells, okay. So we have internal resistance 1 ohm and EMF E1 equals 2 volt, okay. Next we have cell having EMF E2 equals 1 volt and internal resistance R2 equals 2 ohm. So we have two cell, okay. Now what do you find from the question? Their positive terminals are joined by a wire of 10 ohm. So the positive terminal of these two cells, okay, are joined by a wire of resistance 10 ohm and the negative terminal by a wire of resistance 4 ohm. So the negative terminals are joined by a resistance of 4 ohm. A resistance of 10 ohm joins the midpoint of these two wires. So let's say this is the midpoint and this is the midpoint. So the midpoint of 10 ohm and 4 ohm is joined by a wire, okay, having resistance 10 ohm. Now we are asked to calculate the PD between the ends of the wire. Okay, we are asked to find potential difference between these two ends. So we can redraw this diagram in this way, okay. So we can have this, okay. So 5 ohm and 5 ohm in series, okay, gives 10 ohm, okay, and 2 ohm and 2 ohm in series gives 4 ohm and the midpoint, okay. So the midpoint is joined by a wire having resistance, okay, 10 ohm, and let this point be P and this point be Q. So we have this, okay. So we are asked to find, okay, potential difference between P and Q. So we are asked to find this, okay. We are asked to find this. Now let I1 be the current given by this cell and I2 be the current given by this cell. Now in order to solve this numerical problem, we use Kirchhoff's law, and we know we have two laws for Kirchhoff's. One is, okay, first law called KCL, okay, and we have another, okay, called KVL. So this is Kirchhoff's current law and this is Kirchhoff's voltage law. So we apply this law, that is first law or KCL, at junction, and we apply KVL to the loop or closed circuit or closed path. Now as I said earlier, we use Kirchhoff's law. So what we do is that in order to apply Kirchhoff's law, we need to look or search junction in this circuit. And what is junction? Junction is a point, okay, of intersection. This is point of intersection, point of intersection of three or more conductor. So we have this, okay. So we can see this is a junction, okay. We can see this is a junction because we have this, and this conductor meeting at this point, and we have this, and this conductor meeting at this point. So we are going to apply, okay, Kirchhoff's first law or junction rule or KCL to junction P or junction Q. So case first, okay. Applying KCL at junction P. And what does KCL state, okay? So from KCL, okay, we have this. Sum of entering current is always equal to sum of leaving current, okay, that is current entering, sum of current entering the junction is always equal to sum of current leaving the junction, or in very short we can write total current at a junction always equals 0. So we have current I1 entering junction P. We have current I2, okay, moving towards junction P. Now we have this branch, okay. So current flowing in the branch PQ is I1 plus I2. Let us take this, okay. Let us take this. Let us take this direction for current, okay, and solve the numerical problem. So we have this. Now, if you see in the branch PQ, okay, at point Q, what we find? At point Q, we find this I1 and I2 will divide into two parts. One, I1 flowing along this direction. Next, I2 flowing along this direction. So we have this. So this is how we apply, okay, Kirchhoff's current law at junction Q. So we have this. Now, I'm erasing this, okay. Now, let us take, okay, this as loop 1. The upper part of the circuit is loop 1. Let us call the lower part of the circuit as loop 2. So applying KBL to loop 1. Okay, so I'm drawing or redrawing loop 1, this is 5 ohm, and this is R1 equals 1 ohm, E1 equals 2 volt. This is Q. This is 2 ohm. And in this part, okay, of loop 1, we have current I1. Clear? You need to understand this, okay? In this part of the loop 1, we have current I1. So I1 is the current given by cell having EMF E1 equals 2 volt. Now, if you see the branch PQ, okay, this is P, this is Q. Then in this part, that is PQ, we have current I1 plus I2 flowing from P to Q. So we have this. Now we are going to apply KVL, and it states that for a closed path, summation V equals 0. So we have this. Okay, we have this. Now, let us discuss in brief about the sign convention. Okay, so for KVL, this is cell having EMF E. Now, if we travel or move in a closed path in such a way that we are moving from positive terminal to negative terminal, and we know positive terminal, okay, this represent high potential, and negative terminal represent low potential. Okay, so I'm writing in short. So if we move from high potential to low potential, okay, so this is the direction of motion, then this EMF is taken as negative. So this is the sign convention, okay, which we apply, okay, while discussing Kirchhoff's voltage law to the closed path for the cell. Now, if we move, okay, along this direction, let's say if we move from, okay, negative to positive, that is if we move from low potential to high potential, okay, then EMF is taken as positive. So this is to be noted, okay. Now next, what we do for this condition, okay, let's say we have resistance R, okay, and current is flowing along this direction. Let's say current is flowing along this direction, and we are moving along the direction of current. So it means that this side is at higher potential and this side is at lower potential. So if we are moving along the direction of current, okay, and if we are finding the product I times R, then this product is taken as negative. Okay, so this is to be noted. And next, okay, and if we move, let's say if we move let's say if we move opposite to current, we are moving opposite to current, okay, then what do you find? We know current is flowing along this direction. Current is flowing along this direction. So this side is positive or high potential, and this side is low potential, that is negative. So we are moving from low potential to high potential. And if we are finding the product I times R, then this is taken as positive. So these are the sign convention, okay, we use while solving, okay, the numerical based on Kirchhoff's law, that is Kirchhoff's voltage law. Okay, now as I said earlier, this is loop 1. Okay, now let us move in this loop in anti-clockwise direction. We are going to make an equation, okay? We are going to make an equation for loop 1 and 2, and we solve equation and find the potential difference, okay? Finally, okay? Now what we do, let us call this as the start point. This is the start point. So this is start point. We move along this direction. Okay, this is the motion. We move along this direction. We move along this direction and finally come to the start point, so that we make one complete, okay, journey in the given loop. Now, what we do from Kirchhoff's voltage law, summation V, that is potential drop, equals 0. So we are moving from negative to positive of this cell. So the EMF is taken positive, okay? So this is positive. And we are moving along the direction of current, okay? And if we find this product, okay, 1 times I1, then this is taken as negative, okay? If we move along the direction of current and find the product I times R, then it is taken as negative. So we can write in this way, okay? We can write this in this way also. One times I1, and see, we are moving along I1, and if we find the product 5 times I1, then this is taken as negative. And for PQ, okay, we are moving along the direction of current I1 plus I2. So, and we are finding the product 10 times I1 plus I2. So if we find this product moving along the direction of I1 plus I2, then this is taken as, okay, negative. And for this part, okay, we are moving along the direction of current I1, okay, and if we find the product 2 times I1, then this is taken as negative, and this whole sum equals 0. So we have this. So what we do is that now, okay, on rearranging, we can write 2 equals I1 plus 5I1 plus 10 times I1 plus I2 plus 2I1. So 2 equals I1 plus 5I1 plus 10 times I1 plus 10 times I2 plus 2I1. Now we have I1, okay, terms containing I1. Let's see. So what do you get? 10 plus 5, 15, and we have 1, 16, and 2, 18. So what do we get? 2 equals 18 I1 plus 10 I2. So we can take common, and finally we get 9I1 plus 5I2 equals 1. So we get this. Okay. So let's call it equation 1. So from loop 1, okay, applying Kirchhoff's voltage law, we get this equation. Okay. So I'm writing or rewriting equation 1. Okay. So this is by taking loop 1. So we have this. Now, again, okay, we apply Kirchhoff's voltage law to loop 2, okay? So I'm erasing this. Applying KVL to loop 2. Okay, now for loop 2, let's see. So we have this 5 ohm, this is 10 ohm, 2 ohm, this is P, this is Q, R2 equals 2 ohm, E2 equals 1 volt. So in this part, okay, we have I1 plus I2. So keep in mind, okay, we have this. So let me draw in this way, okay. In this part of the circuit, we have current I1 plus I2. And in this part, okay, we have current, okay, we have current I2. So this is to be noted, okay, noted. Now, this is loop 2. Now we are going to apply KVL, okay. Summation V equals 0. We are going to apply KVL to loop 2. So in order to apply KVL, we need to move in the loop. So we can move in clockwise or anti-clockwise direction. So in loop 1, okay, we have moved anti-clock. So let us follow the same direction, okay, anti-clock. And let us call this as the point of start. So this is point of start. So we move along this direction, okay. So we move along this direction and finally come to the point of start. Now what we find, okay, what we find in the branch PQ, okay, we are moving opposite to current I1 plus I2. So if we find the product 10 times I1 plus I2, okay, moving opposite to the direction of current, that is I1 plus I2, then this product is taken as positive. So this is positive. And in this part, okay, in this part of the circuit, we are moving opposite to the current I2. And if we find the product 5 times I2, then this product is taken as positive. Now, again, in this part, okay, of the circuit, in this part of the circuit, we are moving opposite to current I2. And if we find the product 2 times I2, okay, if we find this product 2 times I2, then this product is taken as positive because we are moving opposite to current I2. Now for the cell having EMF E2, we are moving from positive to negative. So if we move from positive to negative, then EMF is taken as negative. So we have E2 negative, okay? Now for this part of the circuit, okay, or this part of the loop, we are moving opposite to I2. See, I2 is moving down and we are moving up. And if we find the product 2 times I2, okay, moving opposite to I2, then this product is taken as positive and this whole sum equals 0. So on rearranging, we can write 10 I1 plus 10 I2 plus 5 I2 plus 2 I2 plus 2 I2 equals 1. I'm taking this 1 on this side, okay? So we can see. So we have this, okay? Terms containing I1. So 10 I1 plus 10 I2 plus 5 I2, 15, and we have 2 I2, 17, 18, 19. So we have 19 I2 equals 1. So let's call it equation 2. So we get this equation, okay, on applying Kirchhoff's voltage law, okay, to loop 2. Now we are going to solve equation 1 and 2, okay, and first find the value of current I1 and I2. Then we find the potential difference V, P, Q. So I'm erasing this, okay. I'm rewriting equation 1 over here. 9I1 plus 5I2 equals 1. Equation number 1. And equation 2 is 10I1 plus 19 I2 equals 1. This is equation 2, okay. So I'm erasing this also. Now let us solve equation 1 and 2, okay. So in order to solve it, what we do, let us multiply this, okay. Equation 1, both sides by 10. And let us multiply equation 2, both sides by 9. This is equation 2. And let us subtract, okay. So we have this. So what do we get? The first term, okay, we can see 90 I1, and this also gives you minus 90 I1. So this cancels out. So I'm not writing this, okay. So we get this. The first term cancels. So the second term is, second term on the left hand side, 50 I2 minus, let us find this, okay, 19 times 9 equals minus 171 I2. So this gives me 10 minus 9. Okay. So finally, on right hand side, we can write 1. So we get this, okay, minus 1 to 1, I2 equals 1. Therefore, I2 equals minus 1 by 1 to 1 ampere. So this is the current. So why we are getting negative? Now we need to know this, okay, or we need to understand this. We are getting negative, okay, because we are choosing current I2 in this direction. The actual direction for current I2 must be opposite to this. Okay, we are getting current I2 negative. Okay, mathematically we are getting this equation. So we are getting this current negative because we have chosen current I2 in this direction. So it's correct direction. Okay, the correct direction for I2 is this. The correct direction for I2 is this. It must be along this direction. So this is to be noted, okay? So this is the original direction for I2. So therefore, I'm writing the negative sign indicates that the correct direction for I2 is opposite to that of direction taken or direction chosen. So we have this. So don't get confused when you get current in negative. So if you are getting current in negative, then the direction of current, okay, must be opposite to the direction of current you are taking or you are choosing. So this is to be noted, okay? Now I'm erasing this. Now we want to find I1, okay? To find I1, putting I2 equals minus 1 by 1 to ampere in equation 1, okay? So equation 1 was this, okay? 9 times I1 plus 5 I2. So I'm erasing this, okay? So that you don't get confused. So this is on multiplication, okay? So on for solving, I2 equals 1. This is equation 1. Okay. Now what we get? 9I1 plus 5I2 is minus 1 by 1 to 1 equals 1. So 9I1 equals 1 plus 5 by 1 to 1. So 9I1 equals 1 to 1 plus 5 divided by 1 to 1. So I1 equals 1 by 9. So we get this 126 divided by 1 to 1. Now let us simplify this, okay? Let's see. 126 divided by 9, okay? So let's do this first. So we get this, okay? 9 times 14 gives 126. So we get I1 equals 14 by 121 ampere. And we are getting I1 positive. It indicates that we are taking the correct direction of I1, okay? We are not getting I1 negative. See, we are getting this I1 positive. It means that the direction of current taken, that is I1, is correct. So there is no correction for the direction of I1. So this is to be noted, okay? Now what we do? We want to find current in the branch, okay? So I'm writing over here. Current in branch PQ equals I1 plus I2. So I1 is 14 by 121 and I2 is minus 1 by 121. So we get this. So this gives 13 by 121 ampere. So we are getting this. Now we are asked to calculate the PD between the ends of the wire. That is potential difference across PQ. So I'm erasing this, okay? So potential difference across, let me write in this way, okay? PD between the ends of wire PQ is VPQ equals current I1 plus I2 times this 10 ohm, okay? So VPQ equals current. So we can see current in the branch PQ is 13 by 121 ampere. 13 by 121 times 10. So let's find this, okay? So we get 1.07 volt. So we get potential difference between P and Q is 1.074 volt. So this is the final result, okay? Now, I'm erasing this. We can also solve this numerical, okay? See, I'm writing over here, okay? From this theory or circuit, we are getting I1 equals 14 by 121 ampere, okay? And we are getting I2 equals minus 1 by 121 ampere. So we are getting this too, okay? You can also solve this numerical by considering, okay, this diagram, okay? Let's say So let's say this is current I1. So we have solved this circuit, okay, by taking I1 and I2, okay, in this direction. I1 along this direction, I2 along this direction, and what we find, I2 is negative. It means that the correct direction for I2 must be opposite to the direction chosen. Okay, so the correct direction. So I'm indicating in this way with the red, okay, ink. This is the correct direction for I2. Okay, now we can also solve this numerical by considering, okay, this direction for current. Let's say I1 is flowing along this direction, and this is junction P, this is junction Q, okay, and we apply Kirchhoff's law, that is KCL and KVL. Now current I1 on reaching junction P, okay, is divided into current I2 flowing along the branch PQ and remaining current. So what do you find? Remaining current, okay, current flowing or remaining current is I1 minus I2 flowing along this path. So what do you find? Okay, we find this I1 current is entering to junction P, and I2 is current leaving along this direction, okay, and the current flowing along this direction, okay, current flowing along this direction is I1 minus I2. We have this, okay, sum of current equals 0. Okay, let's say, or let's understand in this way. Let's understand in this way. Current entering, let's say current in this direction is X, or in this part is X. Okay, and we can choose X along this direction, or we can choose X along this direction. So we have a choice. Let's say we are choosing X along this direction. So this is the direction of current flowing, okay, in this part of the circuit. So what do you find? Current entering is I1. So I'm writing over here. Okay, and entering current is taken as positive by applying sign convention, okay, and current leaving is I2, and this is taken as negative, and current leaving is X, okay, and this is taken as negative, and this whole sum equals 0. Okay, total current at a junction is 0. So we find this. Now we can write I1 minus I2 equals X. So this X equals I1 minus I2, and we are taking X along this direction, that is I1 minus I2 along this direction. So we have this. So we can solve this numerical problem by considering, okay, I1, I2, okay, and I1 minus I2 along this direction. The positive terminals of a battery of EMF 4 volt and internal resistance 4 ohm and a battery of 2 volt and internal resistance 1 ohm are joined by a wire of 10 ohm. The negative terminal are joined by a wire of 8 ohm. The middle point of 10 ohm and 8 ohm wire are connected by a 6 ohm wire. Calculate the current in 6 ohm wire and terminal PD of each cell. So let us draw the circuit diagram, okay, of this question, okay. So we have two cell, okay. E1 is 4 volt, R1 is 4 ohm. We have R2, 1 ohm, E2 equals 2 volt. And what we find, the positive terminal of battery of EMF 4 volt and inter resistance 4 ohm and battery of 2 volt and inter resistance 1 ohm are joined by a wire of 10 ohm. So the positive terminal are joined by a wire of 10 ohm. Okay, so we have this 10 ohm. The negative terminal are joined by a wire of 8 ohm. Negative terminal are joined by a wire of 8 ohm. The middle point of 10 ohm and 8 ohm wire are connected by a 6 ohm wire. So the middle point of this, okay, is connected by 6 ohm wire. So it means that 10 ohm is divided into two parts, okay, 5 ohm and 5 ohm. 4 ohm is divided into, sorry, 8 ohm is divided into 4 ohm and 4 ohm. So we can draw this, okay, in this way. We have 5 ohm, 5 ohm. They are connected in series. So the result is 10 ohm. And we have 4 ohm, 4 ohm, and they combine to give 8 ohm. So this is the midpoint, okay, and it is connected by a wire having resistance 6 ohm. Let us call this point P and this point Q. So we have this, and we are asked to find current in 6 ohm wire and terminal PD of each cell. Now let us first assign the current in this circuit, okay. So let I1 be the current, okay, given by cell having EMF E1 along this direction, and let I2 be the current given by this cell, okay, in this direction. So we have this. Now we are going to find current in the arm or branch PQ of the circuit. And in order to solve this numerical problem, we use Kirchhoff's law. So we know there are two laws. One is Kirchhoff's first law, or it is also called Kirchhoff's current law, and this is applied at junction. And next is Kirchhoff's voltage law. So this is applied to a closed path. So this is applied to a closed path, okay? This is applied to a closed path or closed loop. This is applied to a closed loop. So we have this, okay? Now, we can see there are two closed loop. Let us call the upper loop as loop 1 and the lower loop as loop 2. So we have this, okay? Loop 1 and loop 2. Now what we do? We search or look for junction in this circuit. So this is junction, okay? This is junction, and this is the junction, okay? So we apply first law at a junction. Now what we find, okay, at junction P, okay, what we find? We find I1 is moving towards junction P. We find current I1 is moving towards junction P. and we find current I2 is moving towards junction P. Now we want current in the branch PQ. So we know from Kirchhoff's current law, okay, sum of entering current is always equal to sum of leaving current. And what we do, we take entering current by sign convention, okay, by sign convention, okay, for KCL, we take entering current positive and we take leaving current negative. So the current flowing in the branch PQ is I1 plus I2. So we have this, okay, sum of entering current is always equal to the sum of leaving current. So we have this, okay, or we can understand in this way, okay. Let current flow in the branch PQ be X, and let us choose current in this branch along this direction. We can also choose current in this direction also, okay. So what we get? Sum of entering current, that is I1 plus I2 equals sum of leaving current. Therefore, current flowing in the branch PQ is I1 plus I2. So we can write it directly, okay. So I'm writing in this way. So we have this I1 plus I2. Now at Q, okay, at Q, this I1 plus I2 will divide into two parts. One is I1 flowing along this direction and I2 flowing along this direction. So we get this, okay, on applying Kirchhoff's current law, okay, at junction P and junction Q. So in this way, we have assigned current in different branch of the circuit. So we have this. Now, applying KVL to loop 1. Okay, and we have discussed sign convention, okay, while applying Kirchhoff's voltage law. So we have this, okay. Okay, I'm writing in this way. And current in this part, okay, PQ is I1 plus I2, and this is resistance 6 ohm, and this is loop 1. So we have this. And let us move in anti-clock direction. We can also move in clockwise direction, okay. And let us call this as the start point. This is the start point. So this is the direction of travel or motion, okay. And finally, we reach to the point of start. So on applying, okay, Kirchhoff's voltage law to loop 1, okay, we are starting from this point. Now, in this cell, okay, we move from negative to positive, that is from low potential to high potential. So EMF is taken as positive. So we have plus, okay, 4 volt. And for this resistance, okay, we are moving along the direction of current I1. And if we find the product 4 times I1 by moving along the direction of current I1, then this is taken as negative. And for this branch, okay, we are moving along the direction of current, that is I1. And if we find the product 5 times I1, then this is taken as negative. And for this branch PQ, we are moving from P to Q. Current I1 plus I2 is moving from P to Q. So if we find the product 6 times I1 plus I2, then this is taken as negative. And for this branch, okay, we are moving along I1, and if we find the product 4 times I1, then this is taken as negative. And this whole sum equals 0. Therefore, we can write 4 equals 4I1 plus 5I1 plus 6I1 plus I2 plus 4I1. So 4 equals 4I1 plus 5I1 plus 6I1 plus 6I2 plus 4I1. Now, let us add the term containing I1. So what do we get? 6 plus 4, 10, plus 5, 15, plus 4, 19. So we get this, okay? 19 I1. So we have 4 over here on the left hand side, plus 6 I2. So we have this. Let us call it equation 1. So we have this. So I'm rewriting equation 1, okay, over here. 19 I1 plus 6 I2 equals 4. Let us call it equation 1. So we have this. Now, we are going to apply Kirchhoff's voltage law, okay, for loop 2. So I'm erasing this, okay. So let me erase this also, okay. Next, applying KVL to loop 2, okay. So I'm redrawing loop 2 over here. This is Q. 6 ohm. This is 5 ohm. This is E2 equals 2 volt. R2 equals 1 ohm. 4 ohm. So we have I2 along this direction. So in this resistance, we have I2, okay, along this direction, and we have I2. Now, as I said earlier, okay, this is loop 2, and we can move in loop 2 in clockwise or in anti-clockwise direction. So since we have followed anti-clock in loop 1, let us follow anti-clock in loop 2 also. So let's call this point as the start point, okay? This is the start point. So we start from this point and move in anti-clock direction, and finally come to the point of start. So we have this. Now, what we find, okay, if we find this product, okay, 6 times I1 plus I2, we are moving opposite. You can see the motion is opposite to the direction of current. So this product is taken as positive. So this is positive, okay. Now for this part of the loop, okay, we are moving opposite to the direction of current I2. So if we find this product 5 times I2, then this is taken as positive. And for this part of the loop, okay, for this resistance, if we find 1 times I2, we are moving opposite to current I2. So this is taken as positive. And for this cell, we are moving from positive to negative, that is from high potential to low potential. So for that reason, EMF E2 is taken as negative. So we have this -2, okay, or 2 volt, -2 volt. And for this branch, okay, we are moving opposite to I2. And if we find this product, okay, 4 times I2 moving opposite to I2, then this is taken as positive, and this whole sum equals, okay, 0. So we have this. Now let us simplify this, okay. So 6I1 plus 6I2 plus 5I2 plus I2 plus 4I2 equals 2. Now we get this, okay. 6I1 plus 6 plus 4, 10 plus 5, 15 plus 1, 16. 16I2 equals 2. So let's take 2 common. So we get 3I1 plus 8I2 equals 1. Let us call it equation 2. So we have this. Now we are going to solve equation 1 and 2, okay? Solving 1 and 2. So what we get? So I'm writing in this way, okay? 19I1 plus 6I2 equals 4, and 3I1 plus 8I2 equals 1. So let's multiply this by 4 on both sides, and this by 3, and let us subtract, okay? So we have this, we have this. So what do you get? Now 19 times 4, we get 76I1 minus 9I1. So this cancels out, okay? Equals 16 minus 3. So 76 minus 9. So it gives 67. I1 equals 13. Okay, so we get this. Therefore, we can write I1 equals 13 by 67 ampere. So we have this. So we are getting I1 positive. So it indicates that the direction of current chosen, that is I1, is correct. Okay, so we are getting this. Now we need to find I2 also. Okay, so I'm erasing this. Now putting I1 equals 13 by 67 ampere in equation 1, okay? 19, 13 by 67 plus 6I2 equals 4. So what we get? 6I2 equals 4 minus, so let's find this, okay? Minus 247 by 67. So we get this, okay? Four times 67 minus 247. So let's find this. So we get 21 by 67. Therefore, I2 equals 1 by 6, 21 by 67. Okay. So we get this. So what we get? We get so I2 is 7 by 134 ampere. So we get this. Okay, so we are getting this. I2 equals this much, or we can simply write in this way also. 7 divided by 134. So we get 0.0522. So we get this 0.0522. So we get this. Okay, so we get this. Now, we are asked to find current in 6 ohm. Okay, so we are asked to find current in 6 ohm. So I am erasing this. So current through 6 ohm equals I1 plus I2. So I1 is 13 by 67 and I2 is plus 7 by 134 ampere. So let us find it. Okay. Zero 0.19. This is okay. So this is 0.194 0, and we know this ratio, okay, is 0.0522. So let's add this plus 0.0522. So we get this. I1 plus I2 equals 0.2462 ampere. So we get this. So current flowing through 6 ohm is 0.2462 ampere. Now, we are asked to find, okay, we are asked to find terminal PD of each cell. So I1 is 13 by 67 ampere and I2 is 7 by 134 ampere. And I'm erasing this now. Now, what we find, okay, what we find is that cell having EMF E1 is discharging, okay, discharging current. So cell having EMF E2, this is discharging current. Both cell having EMF E1 and E2 is releasing current. So we use this condition, okay? We know terminal PD. Okay, we know this. Terminal PD, V equals E minus I times R. Okay, this is for the condition, okay, this is for the condition when the cell discharge current. And for charging of the cell, okay, for I'm writing for charging of the cell, we use this condition V equals E plus IR. So this is to be noted, okay. This is to be noted. So what do we do? For cell having EMF E1 equals 4 volt, okay. What we find, terminal PD, let's say V equals EMF E is 4 volt minus I1, okay. So we write in this way, I1 times R1, or we can write in this way also, okay. E1 minus I1 R1. So this gives E1 is 4 minus I1 is 13 by 67 times R1 is 4 ohm. Let's find this. 13 times 4 divided by 67. So we have this 4 minus 0.77611. So we get this 3.223, okay, volt. So we get this 3.22 volt. And for cell having for cell or battery having EMF E2 equals 2 volt, okay. Let's say the terminal PD is V dash, this equals E2 minus I2 times R2. So what do you have? E2 is 2 volt minus I2 is 7 by 134 times R2 is 1. So 7 divided by 134. So we have this 2 minus 0.0522. So let's find this. So we get terminal PD of this cell equals 1.94, okay, 1.9478 volt. So we get this. So we have this, okay.